Folks, and welcome back to my basement. I'm here today to record a supplemental lecture for PSQUIF, as I call it, 6243 Intermediate Statistics covering general linear models. We did talk a little bit about this topic in class last week, but just to reorient us to where we are, this unit is all about describing relationships between two variables in which we need multiple slopes to do so. So the first half of it used an ANOVA type example, a grouping predictor variable that had three groups in which we needed to create two new variables and give them each a slope in order to differentiate the means of the three groups. Another situation in which you would encounter the same problem is when examining nonlinear relationships between quantitative predictors and quantitative outcomes. So in this topic, we have three different kinds of effects that I'll show you. Today we're just going to focus on curvilinear and quadratics, but that is one category in which we would have linear and so-called quadratic slopes to create a U-shaped curve. We'll see that in just a second. You can also natural log transform a predictor variable, and the resulting linear slope would then create an exponential curve when you back translate it into its original metric. Later on, we will talk about piecewise slopes, or so-called linear splines, in which we divide a quantitative predictor into sections and fit separate slopes through each meaningful section. And then finally, the last example in this unit will describe how to test the assumption of linearity in fitting a single slope for an ordinal predictor. So for instance, if I have a 5-point scale in which we rate how happy you are, those aren't really numbers, but because it's 5 categories and it's undeniably ordinal, people would be inclined to try to treat it as a quantitative variable. That represents a series of testable assumptions about the differences between sequential slopes, and so I will show you how to address those. So first up, curvilinear then. Even though we are fitting linear models, all of the relationships that they predict do not have to be linear. In many cases, a curvilinear effect may be more reasonable or just may fit better. There's many kinds. This is a topic that I get into in more detail in the longitudinal analysis class. This is the one that meets before ours currently. But for instance, we can have what is known as a quadratic trend, or U-shaped or parabola, which is what you get when you combine two predictors. So the slope of x, for instance, we would call beta 1 its linear slope. Up to this point, we've just said slope. Now we need to be more specific. So beta 1 specifically would be the linear slope of x. If I take x and square it and enter that new squared variable as a predictor in the model, then the slope beta 2 we refer to as its quadratic slope. And this type of form is good for effects that are expected to change directions. So slopes that should go up but then come back down, or go down and come back up. So this is a generic way of describing this example. Another curvilinear trend that you might be interested in is exponential, and I have ish here because I'm mimicking one. I'm not truly creating an exponential trend. And this can be done by log transforming your predictor and then fitting a linear slope of that log transform predictor. So it would look like this, where you would have done the log transformation in a prior data step. I don't have an example of that, but it should be fairly straightforward once you access the log transformation in your software of choice. So in terms of quadratic slopes, there's one rule that I want you to remember, and that to do anything with a quadratic slope and talking about how it changes the linear slope, you need to multiply it by 2. So if you remember physics from high school or college, that's long gone for me, but the words do ring a bell. The idea of a linear and quadratic slope is related to the idea of velocity and acceleration, whereas the intercept would relate to position. So it works out that the quadratic slope that is given to you in your output is actually only half of the rate of acceleration or deceleration of the slope. That's why we need to multiply it by 2 to make it into the full rate of acceleration or deceleration. So I have an example of this. If I have a fixed linear slope that is 4, and that is specifically at x equals 0, given the equation, because another way of thinking about a quadratic slope is that it's an interaction term of x with itself. Therefore, beta 1 becomes the slope of x specifically when x is 0, which is when the extra part would drop out. So if that is my situation, and I have a quadratic slope that was estimated at 0.3, then I could compute the expected instantaneous linear rate of change, as it is called, at each point along x, and it would be twice the quadratic slope is how it increases per unit x. And the twice part comes from differentiation. So if I have an equation that looks like this, for instance, I have an intercept of 50, a linear slope of 4, and a quadratic slope of 0.3. If I compute the first derivative with respect to x, then what that entails is dropping out anything that doesn't have x as part of it, so the 50 is gone, dropping out the x, and so there's one left here, and then the exponent for it comes out in front to multiply the coefficient. That is then creating the second derivative, which is twice the quadratic slope. And if you're looking at this and going, yeah, I don't remember derivatives or instantaneous, that just means it is the slope of the line that is tangent to the curve at that point. So again, the thing to remember, to do anything with the quadratic slope and talking about how it changes the linear slope, you need to multiply it by 2. Here are some examples, and this is the same slide that I'm going to be giving in the longitudinal class next week, in fact. So here, the x variable is time. So this is in a longitudinal context. And the slope at time equals 0, so note the scale starts at 0. Time has been centered so that 0 represents the first occasion. The slope of the line, to the best of my PowerPoint drawing ability, at this point is 4. So the quadratic slope in this example is a positive 0.3. That means for a 1 unit change in x, the slope increases. It becomes more positive by twice the quadratic slope, rendering it to 4.6. It further increases by another 0.6 at time 2, at time 3, and so on. So the pattern that is being created, I would call this accelerating growth. It's a positive slope that is becoming more positive over time. You can think of things like bacteria growth on a sponge that you're leaving in your dirty dishes in your sink. That would show this kind of accelerating positive function. If your slope coefficients are in opposite directions, then that might create the picture on the top right or the picture on the bottom left. So first, if I have a positive linear slope of 4 paired with a negative quadratic slope of negative 0.3, now they're working in opposition. So the same starting slope at time equals 0 specifically of 4 becomes less positive for every unit change in time. So it goes from 4 down to 3.4, down to 2.8, and so on. So the overall pattern here, I would say, is a decelerating function. Yes, people are increasing in this outcome over time, but the extent to which that occurs is slowing down. So this would be like growth that levels off, so to speak, with additional learning or additional training. You can also have the opposite pattern, so a negative slope that's paired with the positive quadratic. These also work against each other. So now the negative slope of negative 0.4 at time 0 becomes less negative by 0.6 for each subsequent occasion. That means that folks are declining, but the extent to which that occurs is slowing down over time. And then finally, if we have a negative linear slope paired with a negative quadratic slope, that's an accelerating function where the slope is negative and it's becoming even more so by 0.6 for each subsequent occasion. So these pictures can show you how linear and quadratic slopes work together, but I think it's also useful to recognize that these are part of the same function. So for instance, if I follow this function in the top right corner out, it's not going to stay up here. It's going to start to come back down. And actually, it's going to be the second half of this picture. So a positive slope that becomes less positive is eventually going to turn into a negative slope that becomes more negative. So this would be the U shape that's a sad face, so to speak. These two also are parts of each other. So I would start with a negative slope that becomes less negative. If I follow this curve down, oops, sorry about that, it's eventually going to turn positive and then it can pick back up again. So I use these 4 categories to describe what happens in reference to the time 0 as the linear instantaneous slope that's given by the model. Is it positive or negative, and does it speed up or does it slow down? In the GSS example data, we are going to be looking at predicting income in thousands of dollars still from chronological years of age. And to build this picture, I used SAS, and I computed the mean income at every unique value of age. It's treated as an integer value in this data set. And those means are plotted by this black line, along with one standard error above the mean and one standard error below the mean. So these are messy. This is real data. You can see a spike here at retirement age, and you can see a little bit of noise otherwise, but I would say that this pattern is a good candidate for a quadratic slope because it looks like age has a positive slope relating to income up until about middle age, at which point older ages translate into less income. So let's see what happens. So if I fit a model for age, the minimum age in this sample is 18 and the maximum is 76. So I'm going to center my age variable so that my income that's being predicted by the intercept is a meaningful value. I'm going to pick the minimum value this time rather than a middle value, so we can talk about what happens as age increases. Or this is a cross-sectional sample, so these are age differences, not age changes, but nevertheless. I have age sub I is my predictor variable, minus 18, and then I have the same thing squared. So age is being given a linear slope as beta 1 and a quadratic slope as beta 2. The beta 0 intercept then is going to tell me the expected income for someone who is 18 years of age. Had I not centered age at 18, beta 0, the fixed intercept, would tell me the expected income for a newborn baby. Not helpful. So in our data, this is going to be estimated at 2.677, so $2,677. Here's the standard error of that conditional mean, and 2.677 is different than 0, which is a p-value we don't typically care about. The linear slope then. This is the slope of age only when the other part drops out. So we would say that this is the instantaneous rate of change, or age difference in this case, in income per year of age, specifically at age 18. So if we go back to the picture for a second, it's the slope of the line right here specifically. If you picture a stick being drawn through the point at 18, that stick is going to change directions. It's oriented to the up, it eventually is flat, and then it starts to be oriented down. So the linear slope is specifically at x equals 0, which is 18, given the way that we've centered this predictor variable. So then the quadratic slope. Actually, let me interpret this one. So at age 18, for every additional year of age, income is expected to increase by $1.2 thousand, and that is a statistically significant positive slope. So at 18, there is a positive relationship such that more age is related to more income. You make more money as you get older. The quadratic slope then gives us half of the rate of acceleration, or deceleration is actually what's happening here, per year of age, but it holds unconditionally across age. That is, this beta 2 applies uniformly across all the ages. And it was estimated as negative 0.02, and it was also significant, so significantly negative. So the pattern that's being created here is one in which income and age go up together, up to a point, and then it's going to switch, and then age goes up, income goes down instead. So we can compute some points of reference to describe what this curve is doing. For instance, we can compute predicted income for any age beyond just what is expected at age 18 as our reference or baseline for the model. So for instance, age 30. Well, the fixed intercept was 2.677, I put that here. The fixed linear slope was 1.223, I put that here. And the fixed quadratic slope is negative 0.02, and I put that here. Now in parentheses are the values of age for which I would like a predicted income. I'm predicting it for age 30, which is 12 years past 18. So that is why I have 12 in here rather than 30. And then 12 squared would go into this piece right here. And the end result, once you do the math, and by do the math, I mean make the software do the math, is a predicted income of $14,540 with this standard error. I can do the same thing for a 50-year-old, in which case I would plug in 32 as the number of years past 18, and their income is expected to be $21,000, so we're moving up quite quickly. But then by age 70, if I plug in 52 for my target age, which is 18 years, 52 plus 18 is 70, let's put it that way, then the predicted income is down to 13.448. So we see that it goes up and then it starts to come back down. So these are predictions. These are dots on the line, so to speak, according to the model. I can also request linear slopes at any age besides 18. And the rule to do so is to multiply the target age for which you want the linear slope by 2. So if I want the instantaneous linear slope at 30, it would look like this. I start with the linear slope, and then I add to it the quadratic slope. It's negative, so it's a subtraction here. And then I multiply the age for which I want the linear slope by 2. And so that works out to be 0.754. So the linear slope at 18 is 1.2. By age 30, it has slowed down to 0.7. So there's still a positive relationship between age and income. It is now less positive by age 30. By age 50, it has switched directions and started to go down the hill onto the negative side. And by 70, it is decidedly negative. So for your homework, I'm not going to ask you to compute predicted linear slopes. I feel like this is a more advanced topic, but I did want you to have seen it before, specifically because I hope to see you in my longitudinal class at some point later. And just as an aside, you can figure out mathematically exactly where the parabola tips over and starts heading down. There's a formula for it, which is the negative of the linear slope divided by 2 times the quadratic, plus the centering constant to put it back into the original scale of age. And so age 48.575 is when the curve hits a 0 point with respect to its linear slope, and it starts going down instead of up. So if we fit that line, and here's some pictures that I made. We have, this is the fit through the means. So I have the black dashed line is what the model says, and then error bars around it. You see that it does a pretty good job for most ages. Again, some noise out here, but I'm not going to worry about that too much at the moment. And then here is a scatter plot of the actual incomes with the fitted line drawn through them. So you can see that it does a decent job at fitting the means, but there's still quite a bit of variability in income that appears to be unrelated to age. In terms of whether or not these two slopes significantly predict income in working together to create this bendy curvilinear function, yes, indeed they do. So the summary of that analysis I would write as F. So that's my test statistic. F is used when testing multiple slopes at the same time against a null hypothesis of 0 in this case. So I have 2 slopes. That's my numerator degrees of freedom. 731 is my denominator degrees of freedom. That's n minus k, sample size minus number of fixed effects. That tells me how many more slopes I have room to add in predicting this outcome variable. My test F statistic is 47. MSE stands for mean square error or mean square residual. That is your residual variance. It is estimated at 169, so that is the amount of variability in income that is unexplained by age that is left over. This F test statistic is significant at a level of less than 0.001. So if our alpha were 0.05, then we would call this significant. And the R-square that was generated by this prediction is 0.114. If I unsquare it, then the R that goes with it as an effect size is 0.338. So another way to say that is that the income predicted by age using this curvilinear function and the real income are correlated at 0.338. And this is what I would report as the model effect size, not for the individual linear and quadratic slopes specifically, because the linear slope is going to change based on your decision about centering, so it's somewhat arbitrary. I would look at the trend or the curvilinear pattern as a whole and compute an R or an R squared for that to give as my effect size. And just one more thing I want to point out here in terms of exponential trends. So what I have here is original time on the x-axis ranging from 1 to 10 in the top 2 figures, and then I have what the model actually was using, natural log transform time on the bottom. So if you look at the black lines on the bottom here, these were generated using a positive linear slope of log time on the left-hand side or a negative on the right-hand side, but note that it's linear, okay? It's a straight line. If you add to it a positive quadratic slope, so the square of log x is what we're talking about here, then that creates this sort of increasing function A negative version of that quadratic slope for log of x would slow it down instead, and you see the opposite with the negative starting. The positive works against it, the negative enhances it. Now, we don't really care about the log transform variable. It's just a trick. It's just a way to create a bendy shape out of a linear model. So if I were to take these predicted outcome scores and then back translate them, or excuse me, I take the log of, let me say that again. The scores are the scores. What we're changing is the x-axis. I'm used to changing y. That's a different class. So if I take log transform time and I back translate it into original time, so exponentiate would be the right term for that. I usually say unlog when I'm talking about it in courses. Then the black line that was generated using just a positive linear slope for log transform time looks bendy. And you can add the quadratics then to change its shape. So in particular, the blue line here looks very close to what an exponential model would predict. So it's still within the linear models family, which makes it a lot easier to estimate, but it has the shape that we want that would go along with the idea of diminishing returns. So for instance, if this were a number of times you did a task, it looks like your scores go up initially, but then they kind of level off when the effect of practice is no longer as useful. And the same thing would happen here if we're measuring decline. The red line would indicate a decline that is sort of leveling off until some kind of 0 point or homeostasis here. Okay, so I'm going to save the piecewise slopes for in class next week and switch gears to look at this corresponding syntax and output within example 3. So I'm on page 6 of 17 here. It's right after the plot that's showing the predicted scores and slopes for all of the 3 groups related to reported working class. So the first thing that I need to do to examine how age predicts income is make my new variable. So the code to do that in Stata is right here. Gen stands for generate. The new variable that I'm making always comes first, and then equals how I make it out of the old variable. So the variable inside my data set right now is called age. If I subtract 18 from it, I'm then going to make a brand new column that I have labeled age 18. That is because my convention in naming predictors is to add the centering constant at the end so that I can remember what 0 means without having to look further back in my code. And checking to make sure the recording is still working. Yes, it is. Excellent. In R, I would do the same thing by also referencing which data set I want the new column to come out of and go to. So example 3 is the name of the data set that I'm working with. $sign separates the name of the data set from the name of the column, the variable, and I'm making a new column called age 18 out of the old one, which is this much, example 3, $age, and then minus the centering constant of 18. And I have a comment here of what that means rather than a formal label as I generated in Stata, because R doesn't play nicely with labels in many of its functions. So I have first syntax and Stata output for linear age as a baseline, and then we'll look at syntax and output for quadratic age. So this is partially a review and partially informative in terms of examining what the quadratic adds uniquely to the prediction of income beyond linear age. So if I start with a model that looks like this, I have beta 0 as my fixed intercept, beta 1 is my linear slope for age, and age has been centered at 18. So that's the 18 version that's going to go into the code here. And I'm also going to generate predicted incomes to use as an example for ages 30, 50, and 70. So first up, here is the Stata syntax and output. Oops, too much. There we go. So regress is the command we're using. Income is the name of the variable that is being predicted. And then I have c dot as a prefix indicating that I want this variable to be treated quantitatively. This isn't always necessary, but it is sometimes, and so I've gotten in the habit of just always doing it so that I don't have to worry about it. Age 18 is the name of my new predictor. And note that if you had put in the original version of age, everything here would be the same. The slope would be the same, but the intercept would be different, because then the intercept would refer to a predicted income level for a newborn, not an 18-year-old. So this is a pro tip when you're doing homework. If you get everything right except the intercept, that points to a centering problem. So make sure you are using the new version of the predictor variable in your analysis. And again, level 95 is an option. So options in Stata happen after the comma. That is asking for a 95% confidence interval, which is consistent with a 5% alpha rate. So the first thing we get is our model summary, and this we can ignore. Because when you only have one slope in your model, the test of the model is the same thing as the test of that one slope. So I have age 18 as my slope down here, that's my beta 1. Its t-value is 5.52. If I square that value, I get the f of 30.52. So this information is redundant, and that's why in example 2 and in homework 2, I said you can ignore this table except for this one number that we need, which is your mean square error or mean square residual. This is your residual variance. And I ask you this in homework to ensure that you have the correct ingredients in your model. So the intercept is 12.34. That's my predicted income for an 18-year-old. That intercept is significantly different than 0. We don't really care about that though. That just means that 12 is not 0. The slope for age then says that as age increases by 1 year, income is predicted to also increase by 0.2, so $200. So this is a linear slope. The model says that your income should keep increasing along with your age forever and ever. That seems somewhat unrealistic. So that's why we're going to examine a quadratic slope on the basis of just what is theoretically reasonable as well as what the pattern of means suggests across age. Here are some LINCOMs demonstrating how to generate predicted outcomes for specific values of a predictor. So for instance, age 30 is generated by saying I need the beta 0 fixed intercept. I need one of those. So there's an implicit 1 right here in the formula that I'm referring to, like that. So I need one of those, and then I need to fill in 12 for the value of age that is to multiply beta 1. So if I do that, there is my predicted income level, there is its standard error, and associated other statistics. I can do the same thing for age 50. I plug in 32 because 32 plus 18 gets me to 50. And I can do the same thing for age 70, where I plug in 52 instead, because 52 plus 18 gets me to 70. In R, I'm going to do the same process. So first up, I'm going to fit my model. I am calling it model lin age, so that is the name of the object in which all these results will be stored. So income is the variable I'm predicting. Squiggle 1 first so that I remind myself that the first thing that is predicting income is always the fixed intercept, plus the centered slope for age referencing 18. So I do not have our output for this model in the interest of trying to not kill too many trees, but we're going to have our output for the next one. You've already seen plenty of examples of linear slopes, I would say, in both homework and examples, so this should be fairly straightforward. But you can also look at the output that is in the download folder where I have it for all models in all software packages. So I'm using a package called Supernova and asking it to print this equivalent sums of squares table. So that's how I get something that looks closer to that. I'm then asking for a summary, which prints the rest of the fixed effects. So this part is what would happen there. And then I have asked for confidence intervals because those are not included by default, and I wanted to match the output that was given in Stata. Then here I'm using a function called GLHT. That stands for General Linear Hypothesis Test, and what it's going to do is do math on my fixed effects. So I'm generating predicted income levels for a 30-year-old, 50-year-old, and 70-year-old, just as I did above, by saying I need one beta 0, and I want to plug in 12 where age goes because I'm predicting age 30, and 12 plus 18 is 30. So the same logic underlies this code as described up above for these LINCOMs. I am then printing a summary in which I'm not asking for any p-value correction as well as a confidence interval. And I'm not going to need to do anything further with this output, which is why I have not saved it as separate objects. I'm just asking for the information to be printed in the output window. Okay, taking a drink of my water. as I have already had my allocation of caffeine for the day. So now if we look at quadratic age, I will show you our output for these sorts of models instead. And the addition is that we have added this new term. So beta 2 is now adding a quadratic slope for age because age squared is the predictor that it's multiplying. So beta 1 is the linear slope, beta 2 is the quadratic slope. And I have some questions in here that we can keep in mind as we're going through this. So for stata, I am adding the new quadratic term directly without having to multiply it ahead of time. So this term right here, c dot age 18, hashtag or pound sign, depending on how old you are, the same variable, that creates the squared term. Or more generally, you can use a hashtag to create interaction terms, which are multiplicative combinations of two or more predictor variables. In R, I'm saving these results under a new term called model quad age, and I have added the same kind of automatic creation of the squared term. It's right here, so this piece specifically, I as a function, and then the variable squared. So the caret 2 does the squaring part. So this way you don't have to create your predictor variables for squared terms ahead of time. As you would in certain software packages, you can do it on the fly, so to speak, or as you go. So first thing we want to look at then is the analysis of variance table. So this is the sums of squares breakdown. And just to review what this table means and what it's telling us, model is what we know. So we can think of this in terms of the analogy of shopping. So this is how much we spent. This is how many things we bought. Numerator degrees of freedom is the number of slopes in the model. This is how much it costs per thing we bought. Okay, we're going to ignore these two rows here. Don't need them. And then error from the model. This is how much it would cost to buy out the rest of the store that we did not buy. And this is how many things are left in the store that we could have bought. So this is denominator degrees of freedom. It tells you how many more slopes could have been added beyond the two that you do have. And then how much everything would have cost divided by how many things there are gives you an average. So then the question is, how good is our average in terms of the things that we bought versus what could have been purchased otherwise? So ideally, you want this ratio to be greater than 1, meaning you got a good deal. Your cost per item is better than this one here. So F is 47 in this example, decidedly significant if P is less than 0.0001. PRE is how we get the R square for the model. So I have summarized all of that in this little paragraph here. We have the F-test says R square is significantly greater than 0. So note that it's not two-tailed in the sense that R square can't go negative. So this is a test of R square greater than 0. F also can't go negative. So these are in squared units. So I'm going to write it this way, where I have the numerator degrees of freedom, denominator, the result of the F, the residual variance, and then the corresponding p-value. And I could tack in the R square at the end of it if I wanted to as well. So the R square tells us that 11.39% of the variance in income is attributable to the linear and quadratic slopes of age. Then we get into the summary, which provides us with our fixed effects solution, as well as a summary of the table up here with the important parts. And note that I bolded everything that you need to keep track of, okay? I'm trying to help you out. For the summary, we have our intercept. This is the expected income level for an 18-year-old, given the centering of our predictors. Then age 18 has a linear slope of 1.22. That is the change in income per year of age as evaluated specifically at age 18. It is the slope of the line that is tangent to the curve down here on this side of the U-shaped picture. Then the way I would talk about the quadratic is by multiplying it by 2 to say what it does to the linear slope per unit age. So in this case, I would say the positive linear age slope becomes significantly less positive, meaning it is slowing down by negative 0.02 times 2. So multiplying the quadratic slope by 2 is the trick here. So for every additional year of age, this positive slope becomes less positive by about 0.04 in total, if I'm rounding here. Here are the corresponding confidence intervals as well. And I wanted to show you how to create predicted outcome values as well as predicted instantaneous linear slopes. Here's the way to do that. So y hat, predicted income, is built from this function. That means, again, there's an implicit 1 here next to the beta 0 that is showing up in the code. So these lincom statements in Stata, or the 1 that's in the first spot for these linear combinations in R. And then I fill in the value of age that I want the prediction for, and then I fill in age squared. So 12 squared is 144, 32 squared is 1024, and so on. I can also compute the linear age slope per any particular age, and the trick to that is to multiply the value of age that you're plugging in by 2 so that you end up with twice the quadratic coefficient doing the work. So I start with the linear slope of age because what I'm trying to predict is a slope, not an outcome value. So the intercept is not part of this story. So I have a linear slope and I need one of those in every instance of this. So this is what it looks like when you factor out age, essentially. We're going to be doing more of this later in the semester, so if this is confusing, stay tuned. I just want you to have seen it once, and then we'll spend more time on it later on. You will not be responsible for this part in your homework. So then I fill in twice the value of age that I want the predicted linear slope for. And I can do the same thing in R. So note, these 3 lines do not include the intercept. They each use one linear slope, and then I have twice the value of age that I want the predicted linear age slope for. I am just printing, again, the summary of this information and not doing anything with it for right now. And here are the results. So these are the 3 predicted values of age that were in the PowerPoints. Let me go back to find those. One second. There we are. So these numbers on that slide, that is slide 29, all came from here. So I have the 3 predicted outcomes, and then I have the 3 predicted linear slopes, and then I have the confidence intervals around each of those things. So I think we can agree that this is going to get tedious real quick. And also, the values that I chose to plot are completely arbitrary. You know, y12, y32, y52. I just picked some points along the range of age, but it would be more useful, I think, to have more points rather than fewer. Fortunately, there is a way that we can automate this process, and so I promised I would show you it, and here it is. So in Stata, I am using something called margins, which is a way to tell it what predicted outcome values you want as a function of your model predictor variables. Now, I don't actually need to see the output because what I'm going to do is put it in a picture. So the option quietly, it's kind of a funny thing. It just means don't show the results. So run it quietly, as opposed to noisily, which is the default, which means show the results. So at is the function that is allowing me to control the range and the increment of the predictor's values. So what this is saying is start at 0 and in increments of 1. So I have here the from by 2 as the way to understand this. Start at 0, in increments of 1, go up to 57. And I did that because I wanted to get the range of age that was in the data set, and I had centered at 18. So I start at 0, end at 57, and that covers this range. Margins plot, then, must be run directly after a margins, and it understands what you're trying to do. So I tell it what I want the x-axis to be, which is age 18, and I'm naming the plot, and I can then save it as a file. So there's a picture file that was created by this command in your downloads folder that shows the end result. The end result of this part of the code generated using margins is right here. So this picture on the left was generated in Stata. This is showing the predicted U-shaped curve relating age to income as predicted by this quadratic function. I also wanted to show you what the change looks like in the linear slopes specifically as another way of describing the effect of the quadratic in this model. So to do this, I've added one new piece of code, dy dx. means I would like the first derivative with respect to this variable. In other words, I'm asking for the instantaneous linear age slope at each of these points, starting at 0 in increments of 1 and going up to 57. And I asked then for it to be plotted and for that graph to be saved as well. And this is the result of that. So what this is a straight line, because what is being plotted on the y-axis is not income anymore, as it was in the plot on the left. The y-axis in the plot on the right is the linear slope at each of these ages. And the change in the linear slope is constant. So the linear slope changes by twice the quadratic per unit time. The linear slope changes linearly, in other words. The quadratic is unconditional, so there's only one thing that it does to change the linear slope. I don't know if that helps or makes it worse, but I just thought I'd share that with you. To do this in R requires some more code, and I had to get some help with this in all fairness, just to be transparent. I'm doing this in a couple different steps here. So the first thing I'm doing is creating a new data set that has the ages that I want to plot. And analogous to what is happening in this code in Stata, just in a different order, I'm saying start at 0, go up to 57 in increments of 1. I am then using predict, which is a base R function that says, hey, can you take the results from this model and apply them to this new data set and create a predicted income for each of these unique values of age in that new data set? I would like to have standard errors that true, that should be blue for some reason. I'll fix that later. And I'd like a confidence interval. Then after it's done, my data set is somehow not a data set anymore, so I needed to put it back in that way. So I changed it back into a data frame, and then I combined the original X values along with the new prediction. So that way I have X and Y together again in one data set. Then I can make a plot. So the result of the prediction is named as this new variable in that data set called fit.fit. The variable that I want for the x-axis is age centered at 18. These are the limits that I want for the x and y axes. I want a line plot, and I want it to use these labels as well. So this just sets up the points on the plot. Then you have to overlay the lines on them, and I did so using this code right here so that we have an upper interval and a lower interval, and then I created a legend for it as well. So I'm saving this to an image file, and this is the image that I created over here. And the other one, this was created in SAS. This is the one that was in the lecture slides showing how well this predicted trajectory fits through the observed means for each unique value of age. And in this case, I'm not going to go to any more trouble to request effect sizes because the R-square for the overall model is a sufficient effect size. So if I go back to that and make sure I can answer my own questions up here, the intercept is the predicted outcome when age is 18. The linear age slope is how income changes per year of age at 18. And the quadratic slope is half the rate of acceleration. Twice the quadratic is how the linear age slope changes per year. R-squared, then, we can think of two different ways. So the R-square is 0.11. I would say that that describes the proportion of variance in income that is attributable to linear and quadratic age. Or I could unsquare it and talk about it as a correlation, in which I would say that, do we have it down here? I know I had it somewhere. It's in the slides. There it is. Yep. Unsquaring that, R-square creates a correlation of about 0.338. So that's the correlation between y hat as predicted by income and the actual income value. So those are the two ways that I would interpret an R-square. Now, last question. The R-square was 0.04 from the linear age model, and it has increased to 0.114. That's a net increase of 0.07. So that is the change in the R-square between these models, in which the linear model is nested within the quadratic, meaning it's a subset. Saying this more concretely, we first had a model that had these two fixed effects in it, and that model had an r-square of 0.04. After we added this new term, the r-square increased by 0.074 up to 0.114. So the question is, how do we know if that's significant? Well, in this case, we do not need to do any more work to answer that question, because the addition to the model is just this one slope. Ergo, if that one new slope that differentiates it from the baseline model of linear only, if that one new quadratic slope is different than 0, then I know that this r-squared difference is also correspondingly significant. They are telling you the same thing. And lo and behold, yes, indeed. The quadratic age slope is significantly negative. Therefore, adding it to the model significantly improved the r-square, and this is by how much? So there we have it. I have a results section as usual in which all of these things are described, and you can refer to this in answering corresponding questions in your homework about how to describe quadratic trends. We will go back over this at least to some extent when I return from my conference, but I wanted to give it to you now so that you can have a shot at your homework if you'd like to get started early. So you should be able to do everything in the homework if you've watched this video, and I will let you know as soon as it is available. It will be happening later today. Thanks for watching. Smash that like button and hit subscribe. And, if I had merch, I'd say buy it. Thanks.